teachers with too many data about the brain if it is not pertinent for their practice. But why would it be pertinent for teachers to know about the brain? I think there are several good reasons. First, I think we want teachers to understand how reading works. What is it exactly that they are teaching? So have a good model of how reading works. Second, I think we want them to understand how the child's brain must change to acquire reading. So what exactly do they have to do to the child's brain? What are they doing every day? Every day the child comes to school, how is the brain changed? Third, we want to understand why learning to read is hard and the multiple ways in which it can fail. Where are the difficulties for the child? Why is it difficult? And fourth, I think we want the teachers to understand that the brain is highly constrained, and therefore we can explain why some pedagogies are better than others in order to achieve the remarkable feat of learning to read. Now, what exactly is reading? That's basically is going to be the subject of my talk today. What is the architecture of the brain for reading? Which are the different steps in this reading process? And in the end, I will derive some consequences for education. So if you had never learned to read, this is how any page of any book would look to you, like the Rosetta Stone, you know. It's basically a texture and nothing more than that, a visual texture. But because you have learned to read, you can turn this visual texture into speech, into a conversation with the dead, a way to listen to the dead with your eyes. And this is really an amazing feat, the invention of reading. It's totally changed our culture, obviously. So how does that work? Well, I'm going to argue... sorry, just a second, because I've lost all of the animations on the slide. I want to... Maybe I talk for a second to it. I think it will be easier if I can go through the successive elements of my slide. I hope this will work. So, if we start with these regions in green on this slide, you've heard a lot about these regions for spoken language. And Ghislaine yesterday told you that these regions are present early on in the child's brain, even in the newborn's brain, or after a few months of age. Basically, the invention of reading consists in accessing these regions through vision. And this is the great invention, creating sensory substitution, basically, a new modality of input into the speech system. And how does that work? Well, basically, we have to create an interface into the speech system through vision. And my work has been focusing on the role of a specific system, the visual word form area. There's probably actually several brain areas that are developing to specifically recognize a string of letters and connect them to the appropriate speech regions. We'll see, I will not have time to discuss the fact that there are also early visual changes, but you have to know that these exist. But most importantly, this area serves as an input pathway into the phonological system. It allows you to connect letters to their sound units, the phonemes, the units of speech, and therefore to decode what is written into a sound sequence. Now, in this lecture today, I would like also to insist that there are other systems that are extremely important, and I will stress two of them. One is the attention system, which controls your attention, your eye movements, and especially in the parietal lobe. And the second one is a system for handwriting gestures, which is in the more anterior part of the premotor cortex, and that allows you to decode handwriting, the gestures that are done for handwriting. And I'm going to argue that all of these systems have to change and may be the sources of failure in dyslexia. I'm going to capitalize very much on what Regine has described briefly yesterday, this big study that we did, where we were looking at changes from illiterate to literate brains. We've been doing a major collaboration, and since we are in Brazil, I'm very happy to mention that a lot of this work was actually performed here in Brazil, to find people who are illiterate just because they didn't have the chance to go to school when they were young, because there was no school available for them. And we've been able to compare their brains, both with fMRI, and I'll show you today for the first time with ERPs, to show what is different in the brain of a person who has learned to read compared to the brain of a person who has not learned to read. A third category of people is these ex-illiterates, who are people who have never been to school but were able to learn to read with their peers or in adult courses, and therefore they are interesting because they provide a pure measure of the effect of literacy without the effect of early schooling. So this is a photo. I really have lost all of the animations. This is really annoying. I don't know if there is a keyboard that would allow me to control them. So when I click, yeah. Well, never mind. You see? Okay, when I go back, it's interesting. When I go back, I can control them.
An X, back, back.
Yeah.
An X.
Bam. Yeah, I get all of them. No, it doesn't work. I get all of them. Never mind. Sorry about that. It doesn't matter. You'll get the ideas. The pictures will not be as pretty. With the help of Dr. Lucia Braga from the Sara Hospital, who played a major role in this work in Brasilia, we went to look for people who had never been able to go to school. We studied them behaviorally first to show that they were really illiterate and they didn't have any developmental deficits, and then we scanned them. And at the same time, at Neurospin in Paris, we brought people from Portugal who didn't have the chance to go to school as well, and we also scanned them at Neurospin. So this is a big adventure, and we found that one of the most important variables to characterize these people was reading speed. Because reading capability itself, obviously only the illiterates, which are the first group on the left here, were not able to read any words. In fact, they didn't know most of their letters. But the ex-illiterates from Portugal and from Brazil were already somewhat good with variability in the ability to read words and pseudo-words. But reading speed was the most important variable changing between these 6 groups of subjects. And even inside the early literates, we had some significant variation as a function of whether these people were from the same communities as the illiterates, or whether they were from, university-style students, and had therefore a lot of training with reading. So we decided that the best way to go was to correlate brain activations with reading speed and look for differences that were due to having learned to read more or less fast. And when we did this, we found that there are many changes in the brain that sort of illuminate the different steps in the circuit. So first thing is this visual word form area system. This is the most easily measurable correlate of reading changes, literacy changes. Here is a view of what happens when you do a 5-minute measurement. You bombard people in the fMRI with a series of words that form very short sentences, such as, it's easy to find a taxi in Brasilia. Very simple sentence. And you correlate reading ability with brain activation. So obviously, the more you can read, the more you activate all of the language areas. This is a picture very similar to what Ken Pugh has been showing, with the activation in inferior frontal cortex, Broca's area, but also all along the superior temporal gyrus, and all of these are shared with spoken language. This is basically showing that when you've learned to read, you are accessing the same spoken language system through vision. But we also have changes in the visual system, and you can see some early visual occipital changes, but especially very strong changes in this visual word form area here in the left hemisphere. The left hemisphere is on the right when you turn the brain, And you can see this very strong increase in activation, especially as soon as you learn to read beyond a certain speed. So the ex-illiterates here, who have learned to read in adulthood, already have very strong activation in the area. The system is still plastic enough to learn to read in adulthood. What do we know about this brain system? This is one of the most important systems for invariant recognition of the written word. First surprising thing is that this area exists in all cultures. Whether you learn to read in Chinese, in Hebrew, in Arabic, in Portuguese, it will show as a specific site with the same, roughly the same coordinates. It is strongly activated by words more than by other categories. In fact, very interestingly, words stand next to faces, and further away there is houses and objects. There is a mosaic of area that Ghislaine showed you yesterday, which is absolutely systematic. It's something very striking that words will occupy the same spot in the brain. Later in my talk I will try to explain that. But it means that we have a very precise system. It will not vary a lot from child to child. Very often when I speak to teachers, I hear that every child is different. Well, this is not the case. There is a very precisely reproducible system for reading. The selectivity for words and letter strings can be very strong. If you have electrodes that are placed inside the brain, like in this case of epilepsy patients, you can find electrodes that will react only to letter strings, or to pseudo-words, or to words, and not to any other category of objects, or faces, or houses. So there is a selective system. It will activate, of course, not to any script. If you have not learned to read Chinese, it will not activate to Chinese. But it will activate to Chinese in people who have learned to read Chinese. So it's being changed by reading. And we know also of a very tight association with reading through lesions. If you have a lesion that affects this region, or maybe affects its afferents, like in this case here, a very small surgical lesion, you may lose quite selectively the ability to read. In an adult subject who was able to read, suddenly reading is gone. The person is not able to identify the written word, but may still be able to recognize faces, to recognize houses or objects, and also to speak, and even sometimes to write, which shows you how selective this region can be for recognizing the written word. Now, we know that this region is doing a lot of the work that's needed for invariant reading. When you look at a page, the words may be in small print or in large print. They may be written in uppercase or lowercase. They may be on the right side or on the left side of your fixation, but you recognize them all. It is this area which is putting the information together in an abstract form that allows you to recognize the abstract identity of the letters and the words without caring for the face, for the case, for the location, for the specific form or font which is being used. Now, why is there such an area? This is still a little bit of a mystery, but I've been arguing for this neuronal recycling hypothesis. The idea is that our visual system is not unlike that of other primates, like the macaque monkey here. We have a chain of successive areas, synapse after synapse, that allow us to abstract away from the specific form on the retina and to access the abstract identity of visual objects. And this pathway is being used in macaques for the recognitions of objects and faces, and in humans we recycle it to add written words to what is being recognized by this pathway. And we know that there are many neurons in this area that encode what we could call an alphabet of shapes. If you record from individual neurons in a macaque monkey, this is not yet being done in humans, but it will come very soon, and I think it will be very interesting. But in macaque monkeys, you already find neurons that care about specific faces, like a profile or a front face, but also specific shapes, like a star, or a T shape, or a Y shape. And amazingly, these are already the shapes of some of our letters. I have been arguing that we selected these shapes because they are very easy to recognize. They are already present in the repertoire, or the alphabet of shapes that are present in this area. So how can we understand how reading works in this area? This is a very simple model that we've proposed already some 9 years ago. The argument is that recognizing a word is quite similar to recognizing a face. In the case of face recognition, we begin to understand that there is a hierarchy of successive neurons. If you can recognize one of these faces, it's because you have sets of neurons that recognize, for instance, the eyes regions, but others will recognize the mouth region and so on. And themselves, these neurons are based on the ability to recognize elementary features. Well, it probably is very much the same for reading. You have a pyramid of successive neurons with increasing degrees of abstraction. At the bottom are the same neurons that recognize elements of faces. So they recognize little contours. But when you put together these contours, very quickly you can have selectivity for T-shapes or curves that if you put together allow you to recognize specific letters. And as you go higher and higher in these degrees of abstraction, you find that there may be neurons that recognize sets of letters, pairs of letters that are next to each other, and therefore create a unique neural code for the written word. For the moment, this is a model. Nobody has recorded any of these specific neurons, specific for a single letter, but we have indirect evidence from priming or from decoding studies from fMRI that suggest that this area has a neural code. So every specific word that you see, when you've learned to read them, you can assign them a specific neural code in this area. There's beautiful work, for instance, from Brenda Rapp, showing that the codes for letters are discriminable in this visual word form area. You see also that calling it one area is maybe a little bit of a mistake because there are several successive steps and they correspond to moving forward in this hierarchy that I showed you on the previous slide. So moving forward in this hierarchy creates more and more degrees of abstraction. Now, what does this area do prior to reading? It's not just sitting there waiting for you to learn to read. It's doing something else and we reconvert it. This is the neuronal recycling idea. So we got direct evidence from that from our study of illiterates. I showed you, and this is replicating with just flashing letter strings that are not words, like ubi here, that the more you can read, the more words you read per minute, with the illiterates being here, the more you activate this visual word form area. So it gets more and more responsive to letter strings. But if we look at the activation to all of the other categories of objects, we see very clearly that these activations, many of them decrease. And this is particularly the case for faces. The face activation decreases the more you can learn to read. There is no change for a false font that looks like words a little bit. So faces and to some extent also checkerboards decrease significantly. And this is accompanied by a measured shift of the face system. We see very clearly that there is an increase in activation to the face system on the right side of the brain, the right hemisphere of the brain. This is quite striking. So the more you learn to read, the more you reorganize your brain. And Ghislaine yesterday showed you that this is the case also in a child's brain. We see this shifting where words compete with faces. Learning to read has to make some space in the cortex for specialization for letters, and that creates a systematic shift of faces away from the left hemisphere and towards the right hemisphere. Several people have replicated this finding now, including a study in Chinese using ERP. So this seems to be a pretty large, maybe universal phenomenon of competition with faces, because we are using the same sort of resources, the same sort of neurons to learn to read and to recognize faces. Now, recycling, this idea that we change a cortical function that exists before reading, can explain some of the mysteries of reading, including something that initially was suspected to be linked to dyslexia, but is not linked to dyslexia. The fact that some children read and write in mirror image, like in this case, you see the child's sign is drawing Leon from right to left, and this is another child that I loved, who has written Theodore Ti voglio bene, okay? So one line is from left to right, another line is from right to left, with some mistakes in between. It's quite amazing that a child has reinvented what is called in the history of writing boustrophedon. Boustrophedon was used in a culture of ancient Greece. If you look at Greek vases, you may still see writing from right to left and left to right. But how can a child know about boustrophedon, about ancient Greek? Of course the child does not, but what the child has is an organized visual system prior to reading that generalizes across left and right. So if you look at these faces, you can immediately see they are the same face because your face recognition system is strongly attuned to left-right mirror images. And this has been shown recently in the beautiful study by Frywide and Tsao in Science 2010. They show that individual neurons if they care about a specific profile, they will also care and respond strongly to the same profile seen in mirror image. All of these neurons in a specific region called AL here, which is a very plausible homologue of the visual word form area in humans, have this property of mirror imaging. So we start with this system in life. There is evidence that even babies have this mirroring system, which is very advantageous because it allows you to recognize mirror symmetrical objects, which are of course very numerous in our daily lives. But when it comes to reading, this is a problem because you have to distinguish these letters and these words. These could be two completely different words, although they are mirror symmetrical. I don't know, you cannot even see, because you've learned to read, you cannot even see that they are mirror symmetrical. It's very hard to see. So we have to unlearn the ancient evolutionary useful function of mirroring, mirror generalization, and direct evidence for that was obtained recently with Felipe Pegado, using the very same subjects, literate, ex-illiterate, illiterates, that we used in our fMRI study. But here it's a behavioral study. We showed them pairs of images, and we asked them, are they the same or not? And they were supposed to say same to these pairs that are mirror images, or to these pairs, or to these pairs, but they were also supposed to say same to these mirror pairs, or to these mirror pairs. And you immediately understand that saying same in these circumstances is not easy for a literate person. And that's exactly what we found. We plot here the mirror cost. Mirror cost means how much slower you are to say same to these pairs compared to identical pairs. Okay? And the more you can read, the more words you read per minute, the more you have this cost, the more it is difficult to say same to these pairs. Because, of course, they don't look the same. All of your training has been to say that they are different. But what's very interesting is this also generalizes to some extent to false fonts and even a little bit to pictures. There's a significant cost here. So remarkably, there is a little bit of an advantage to illiterates here, a sort of relative advantage. They don't have this cost. They have a direct capability to recognize mirror images. We've lost a little bit of that. We've not lost a lot. We have just a little bit of a reaction time cost to decide that these pairs are the same, although they are in mirror image. But this means that there has been competition, and we've lost a little bit of this ability of our visual system because we've learned to read. So mirror imaging ability, if I go back to these errors that I was showing earlier, these sort of errors are not specific to dyslexia, except in maybe in very rare cases, like one publication by Michael McCloskey shows one person that probably had mirroring errors at a specific source of dyslexia. But in most cases, this is a consequence of not having learned to read. And when you learn to read, these errors go away. Now, these studies of literacy that we've done with adult literates and illiterates, they've mostly been done with fMRI, and there was only fMRI in our science paper. But fMRI, of course, cannot tell you about the timing of activation. So recently, we've been also finalizing the analysis of event-related potential data that we've acquired in the very same subjects, in the very same stimuli. And I would like to show you today that we can use this data to understand something about the timing of these effects. And this is very important because fMRI effects could come top-down. But we are arguing that this is in the bottom-up phase of activation that these changes are occurring, that the very analysis of the visual stimulus has been changed by reading. And so in this experiment, what we did here was we flashed the very same stimuli, first a first picture and then a second picture. And it was just passive looking. Subjects were searching for a star. So you can see the ERPs evoked by these successive words, or pictures of faces and so on, all of the same stimuli. And we had three types of trials. The same trials where the two pictures were the same. The mirror trials where there was one picture and then its mirror image. And then the different trials where there was one picture and then a completely unrelated picture. Always from the same category. But this allowed us to look for what is called as repetition suppression. We know that the brain reacts differently when it sees twice the same picture than when it sees two completely different pictures. Here, most of the work has been done already, and so typically there is a reduction in activation. So by comparing the same trials with the different trials, we could get an idea of the ability of the brain to discriminate these objects. If the brain is good at discriminating these two words, then there should be a big difference between same and different trials. And basically this is exactly what we found. As early as from 100 to 148 milliseconds, in this time window, which is quite early, not the earliest we can find, but just after the initial volley of excitation into the visual cortex, we find that there is a very strong repetition suppression effect. And furthermore, that this repetition suppression effect is highly correlated with the reading scores again. So basically the illiterates don't show it. They are not able to distinguish these two types of trials because it's hard, requires training of the shapes of letters. But the more they are reading, the more their brains very quickly distinguishes between these two pictures and is able to tell that this is a different, that this is a different trial. We see also that this effect comes from the early visual cortex and especially the left visual word form sector. We cannot be very precise with ERPs, but this is the correlation map of this effect on the top of the scalp, and you can see it comes from this left inferior occipitotemporal region, and this is the source analysis. You can see also that this effect is very strong for strings, generalizes a little bit to false fonts and to faces, and not much to the other categories. So once again, we have refined the system. There's a little bit of generalization to the other categories. Even more important, we confirm that during the very same time window, we have improvements in mirror generalization. So now we compare situations where we flash a mirror trial and we compare it to the same trial. Does the brain discriminate these two types of trials? If it does, it means that the brain has learned that these should be treated differently. And we find that the brain treats them differently for strings in the same sort of region in the left occipitotemporal cortex. And again, there is a little bit of generalization to false font and especially to faces, not so much to houses and not at all to tools. So there is a system here that has been transformed, and again, there is a strong pairing between strings and faces when it comes to this transformation. This means that the brain has refined the precision of its coding, has become able to distinguish mirror images, a key step in the visual part of learning to read. Now, of course, there are many other changes, and I want to briefly review changes that are occurring also in the auditory pathway for you. So, actually, I don't have to go very slowly because Ken has been showing exactly the same slide from our fMRI study of illiterates. What we see here is that in an auditory region, which is just behind the primary auditory cortical area, so in the posterior superior temporal cortex, in a region of the planum temporale, we see that there is a strong response to spoken language, not much to written language, but the response to spoken language is strongly increased by learning to read. So the illiterates are all the way down here. They have activation, but that activation is almost doubled in the people who are very good readers. And we replicated this observation in a second scanning session where the subjects were doing single word and single pseudo-word lexical decision. So this is sentences, this is single items, but again you see the activation is strongly increased by learning to read. So massive change in this area. We are pursuing this finding. We don't really know what it means, but we sort of know what this region is doing. And in particular, I want to call your attention to the beautiful work that is done by Ed Chang. Using intracranial electrodes in epilepsy patients, he's able to have very fine recordings in his general area of the superior temporal cortex. And some of the recordings, like here, are done strictly in the planum temporale. And what he finds is that there is a neural code for phonemes in this area. It's actually to the point where you can find that individual electrodes, when they're fine enough, respond to specific phonetic features of speech. So, for instance, you'll find an electrode that responds to plosives, and not only to plosive, but to specifically to coronals, for instance. Other electrodes will respond to fricatives. Other electrodes will respond to specific vowels, like vowels that are pronounced on the back of the mouth. Others will respond to nasal. So there is a combinatorial code, just like we believe there is one in the occipitotemporal cortex for vision, but now it's a code for phonemes. And our data suggests that this code may be changed by learning to read. Our observation suggests that maybe phonological awareness leads to a stronger discrimination of phonemes and increasing of activation to speech in this area. So a second major effect of reading. There is also beautiful work that should be mentioned here by Leo Blommert, who unfortunately died way too early, and was doing these beautiful studies. And you can see the high convergence between what we found and what he found. What he found was that activation by a sound is modulated by whether there's a congruent letter presenting at the same time. So you hear the sound A, and at the same time you are presented with the letter A, or you are presented with the letter O. Okay? When the two are when the two are congruent, you get much more activation in this area than when the two are incongruent, which suggests that this area is integrating the information cross-modally from the written letter and from the spoken sound. And very interestingly, this effect is not found in dyslexic children. There is a lack of proper integration, perhaps as a consequence of not learning to read. We don't know whether it's cause or consequence, but it's a very interesting observation that this is one of the major features, let's say, of dyslexia, inability to have this convergence between written letters and spoken sounds. So I told you that there are changes in the ventral visual system, changes in the dorsal auditory responses. We may think that there should be changes in the connection between them. So this is very natural thinking that's, and of course it's derived also from many models, such as the model that was shown yesterday by Joe Ziegler, that the connectivity between vision and the language areas should be changed by learning to read. We thought that our study of illiteracy was also perfect for that. We collected in the same subjects what is called diffusion tensor images, which allow you to look at the connections of the brain. We tracked these connections. This work was done by Michel Thiebaud de Schotten, who is a specialist of diffusion imaging and tracking. You can see some of these fiber tracks that we were able to extract, long-distance fiber tracks that have different names. We analyzed them for their inner organization with a parameter called anisotropy. And what we found was that one of these pathways, the yellow pathway, was being modified in correlation with reading score. So reading score predicted the organization, the fractional anisotropy of this pathway. And this is the vertical part of the arcuate fasciculus, which links the ventral temporal regions with the more dorsal superior temporal and inferior parietal regions. So it's perfectly appropriate for at least a subpart of it to mediate from vision to higher level auditory representations and auditory working memory. And there are several very interesting observations here. One of them is that even alphabetized adults show this modification. So, I mean, the ex-illiterates. So people who have never been to school but learn to read in adulthood, they have this changed, which means that the system is plastic enough for connections to be changed in the brain. Now, what could be the interpretation? We know that axons are surrounded by sheets of myelin, and most people believe that changes in fractional anisotropy may reflect changes in myelination. One factor that goes towards this interpretation is that we found a change in transverse diffusivity perpendicular to the fiber, which is exactly what would be impeded by more myelination. There is no change in longitudinal diffusivity. And we also found that these changes were correlated with the changes in activation in the ventral visual system and in the more dorsal auditory activations. Both were making independent contributions to changes in anisotropy. So this suggests that this pathway is changed in direct proportion to how much the visual and the auditory changes have occurred in the same brains. So there is really a strong case to be made for this notion of a complete change in the circuits, both in the visual part, in the connection to the auditory part, which is also changed. Now, this notion that the connectivity of the system is crucial and that there is an area that connects preferentially to the language system is, I think, a very important point. Remember, I told you there is a mystery. Why do we have a specific brain area for reading in the occipitotemporal visual word form area? We never evolved for reading. It's a very recent ability. We do not have genes specifically for reading. So why do we have a mental organ, a brain region specialized for reading? Well, I think we can understand it from its connections point of view. That this area has specific connections to the language system, and we just use it, we recycle it, because it has this connection. In fact, the invention of reading was possible only because we have in our brains connections that link vision to language. So recently we pursued this idea by looking at diffusion tensor tracking and looking at what are the connections from the visual word form area. So this is a study where 80 subjects were tracked. We started from the visual word form area and we followed all these tracks to see where they are going in the cortex, and the color areas here show you the targets of these connections in the cortex. So where do they go? And we see immediately that starting from the visual word form area, we go, of course, to the ventral visual pathway further on and further back, but we also go to the superior temporal sulcus, and we go to the inferior temporal gyrus, all of the language areas that are needed in order to understand spoken language. And is this unique to the visual word form area? Well, to some extent it is. It's not unique, but it's stronger at the visual word form area site. So what we can do here is we make an image of where in the cortex do we have stronger projections from the visual word form area, starting here, than from the nearby FFA, the fusiform face area. I told you they are side by side, words and faces, but always in the same locations. So if we track from one, or if we track from the other, do we find the same systems? No. If we track from the visual word form area, we find more connections to all of these regions, which are predominantly language areas. And vice versa, if we track from the fusiform face area, we find predominant projections to these more mesial systems, including the amygdala and the anterior mesial temporal areas that have to do with face recognition. So we think we understand why the visual cortex specializes for reading or specializes for faces. It is because it is part of a circuit, and the most useful neurons for language are located at slightly different locations from the most useful neurons for face recognition. The circuits are already there in the young child, even in the baby. As Ghislaine showed you yesterday, the main circuits are all there at birth, and they serve as a sort of shaping for the learning that occurs later on, and they can explain the locations of these areas. There is further research along these same lines. For instance, here across many different subjects that are all right-handed, we can see whether the variation in the lateralization of spoken language predicts also the lateralization of the visual word form area. The visual word form area is usually on the left side, but what we find here is that the more the subjects are right lateralized for language, the more the visual word form area is also right lateralized. And this has been taken to one extreme by Ching Tsai, who showed that if you find subjects that have complete right hemisphere lateralization for spoken language, then we also have a right lateralized visual word form area. So once again, the visual word form area is following the circuits and the connections of the language system. And we can take that to another extreme with blind subjects. This is really the most extraordinary studies that have been done by Amir Hamedi in Israel. What is done is take subjects who are blind from birth and look at how they read in Braille, or how they read via a completely new system that is invented to read through the auditory pathway. So this is, of course, an extreme case of neuronal recycling. You are going to look at what activates when people recognize images and written words by audition. How does this work? Subjects have a little camera. Camera films the scene and translates it into a sound. The sound goes across time, from left to right, scans the image, and the vertical dimension of the image is coded by frequency. So if there is something high in the picture, there will be a high-pitch sound. If there is something low in the picture, there will be a low-pitch sound. But you can code the entire face by having a sort of chirps like this. Okay? And they learn to recognize the sound as an object. After a few weeks, they can do this, and once they can do this, you can scan them with fMRI while they listen to the sounds, but the sounds can depict letters, or can depict faces, or houses, or objects, or body parts. And what you find is that there is an amazing form of specialization in the visual cortex, although they are only listening to the sounds, but they interpret them as visual stimuli, as pictures, they activate the visual cortex, and furthermore, they activate specifically the visual word form area when they are reading, when they are recognizing letters. What this means is that perhaps the visual word form area is not very well named. It is a word form area, but the visual part is not so important. What's important is its contribution to recognizing shapes that can be mapped onto speech. Whether they are from touch or from audition, the same circuit will be used because this is a circuit that connects to the language system. So, summary of what I've said so far: reading acquisition specializes the cortical area for the fast recognition of letter strings, graphemes, and establishes a functional link with areas coding for speech units, phonemes. Initially, this is essentially what Joe has been telling you yesterday. Children will decipher the words using the yellow pathway. They effortfully analyze the words, they convert graphemes into phonemes, they listen to what they get, and they understand the corresponding words if they have the word in their vocabulary. So they go through this sort of slow route of conversion. Progressively, they will learn to assemble the letters together and go through a more direct route. And as Joe was showing yesterday, this will be a very progressive training of the system to go more directly towards the meaning and the lexical representation of the words. It's important to notice for teachers that you don't need to explicitly train the green route. There will be self-teaching, self-training, as exactly as was shown by Joe yesterday, as long as the child masters the yellow pathway, which is the decoding, and has the ability to convert what has been decoded into a lexical unit and a meaning. So this diagram, I think, which is extremely simple, can help also explain what are the variables that will ultimately influence the child's ability to learn to read. We know that several of these variables include knowledge of phonemes, child's vocabulary, and the presence of books in the child's surroundings. And all of these are things that we can manipulate in preschool, of course, to facilitate acquisition of reading. Why do these variables influence? Because the child must have phonological knowledge in order to have an efficient pathway here, and knowledge of grapheme phoneme conversion, but it must also have high vocabulary to understand what is being written, and it must also have many books to have a lot of training of this circuit so that the green circuit is put into place. Very simple image. I'm sorry for my colleagues if I simplify too much, but I think it helps to store in our brains, in the brains of teachers, what is reading. Now, I want to finish in the last 2 minutes by telling you about these two more components of the reading circuit: special attention scanning and gesture decoding. I've told you mostly about the adult fluent reading circuit and what has been changed if we compare adult illiterates versus adult literates, but fluent reading is not always the case. We know of many ways to degrade reading, and in this experiment with Laurent Cohen, we've degraded reading by spacing the letters, by moving the letters to the left hemifield, which is not good at reading, or by turning the words. If you turn the page beyond 45 degrees, it becomes hard to read. And we predicted from our knowledge of the visual circuit that, for instance, beyond 45 degrees of rotation, the cells in the occipitotemporal pathway should no longer respond and be able to recognize the written word. And this is exactly what we got. These are adult subjects. They can read very quickly all of these words up to a specific threshold, and beyond that threshold, suddenly reading slows dramatically, and especially subjects become submitted to the word length effect. So you see words of 4, 5, or 6 letters, they begin to have a very strong effect on reaction times. Subjects moved to this very slow reading, where we found, using fMRI, that there is an additional circuit that kicks in when you have to make an effort to read letter by letter in these conditions. And it's the same circuit for all of these three conditions. It is the left and right bilateral parietal regions that are in the control of attention and eye movements. And these areas also amplify letter representations in the ventral visual pathway. What is happening here is that we turned an adult reader into a child reader. We forced an adult subject to go back to this slow mode, which is characteristic of beginning readers, where you have to go slowly to assemble these letters. And we know this is extremely important in the course of reading development. And in fact, for many, many different types of learning, including arithmetic learning, for instance, very often you see two stages. First, there is very strong involvement of parietal and prefrontal networks for attention, strongly activating during a phase of slow, explicit, effortful processing, and progressively the circuit will automatize, these areas will disappear, and we'll see an increase in more ventral posterior systems. This is very clear in the case of reading. When you measure the speed of reading, the number of words read per unit of time, so the time taken to read a word, and here you have the number of letters of the word. You can see very clearly that the more the number of letters, the more the beginning readers, as well as the dyslexic, need time in order to read it, just like our adult readers. And then automatization sets in, and by second grade and third grade, they become very flat, and adults are just completely flat. They can read in parallel. Well, this automatization is one of the essential systems for reading. Why is it crucial? Because you want to free the systems of parietal and prefrontal areas from the effort of deciphering the words before the child can concentrate on the meaning of the message. So, for instance, what is the story about, or what is this mathematical problem about? So automatization is an absolutely crucial step, and these parietal areas are playing an essential role in this system. I should also say that sleep is absolutely essential here. So as we are giving recommendations to teachers and parents about the reading system, we should mention that there is considerable neuroscience research these days showing that sleep is an essential phase where consolidation of learning is taking place. And many problems ensue if you deprive a person from sleep because she is not able to consolidate what she has learned during the day. So we can recommend that sleep should play an essential role in the organization of a child's routine during learning. Although I don't know of any direct study of how sleep influences this sort of consolidation for reading. It would be very interesting to look specifically at reading. But there are many studies for all sorts of motor or sensory activities that show the effect of sleep. Now, I want to finish a little bit over time with the last circuit I wanted to tell you about, the circuit for handwriting gestures. This is something we've found recently in our work, but it's been hinted in many previous work, that we've always studied printed letters. But of course, for a young child, the most important is often to be able to recognize handwriting. And even for us as adults, we are challenged. Our reading system is quite challenged when we have to read handwriting like this. And you may even feel that in order to decipher this, you have to sort of guess at what was the gesture that was done by the person, in this case, Darwin. This is Darwin and handwriting. There is an area that's called Highness area, which is in the left premotor region, that has been claimed to be unique to Chinese, but very briefly, we found that it is also involved in alphabetic reading, but specifically when you have to read handwritten letters and decipher the handwriting. So I won't have time to describe to you the study, but basically we presented not static letters, but letters that are presenting dynamically in the forward or in the backward direction compared to static. And the same experiment was done in French and Chinese subjects, and we found a complete double dissociation where the visual word form area was active for static, normal shapes, as I told you earlier, but there was this entire additional premotor system, including this Highness area, that was activated specifically by trajectories that were in the forward direction. And that seemed, therefore, to be able to decode what was the gesture that had led to the written word when it is a handwritten word. And of course, that system is not very useful when it's a printed word, because the shape of the letters don't have any relation to the handwritten gestures, except in Chinese. And we think this is why people saw it in Chinese first, because in Chinese, the printed characters look like they've been handwritten. So anyways, this is not a Chinese system, it's a universal system. It's there in French readers, in alphabetic readers. It's very useful whenever we have to decipher handwriting. And there is a lot of pedagogical research which is showing, convergent with these anatomical functional imaging findings, that learning to write is playing a very important role in young children. Children who learn to write, or at least to trace the letters at the same time as they are learning to read, have benefits and benefit from being able to have an additional neural code for storing the shapes of letters. So this is another recommendation that we may give to the organization of early reading education. Learn to read, learn the gestures of writing at the same time. So this is my conclusion. I've shown you all of these systems, but clearly I want to add the importance of this attention and handwriting gestures to the story. And I will just conclude by saying that we've tried to put together with several colleagues, at least in French, recommendations for teachers. I will not have time to review them all, but I want to summarize that we can recommend the explicit teaching of grapheme to phoneme conversion rules, because this is the heart of the circuit that is present in everybody's brain. There's not a single child that doesn't have to go through this circuit. But we can also add that the teachers must have a very careful guidance of visual attention, left to right, systematic, in order to train this attention system. And we must also have an active learning system associating reading and writing. It's very important to have daily practice so that we can have training that will move from effortful to effortless reading, and the role of sleep is essential in this process. And finally, I think the work that I've shown you implies that reading is not the feat of one brain system. There are multiple brain systems that are all collaborating to create reading, and therefore I expect, and I think there's a lot of backup for that, for instance in the work of Joe Ziegler, that different types of dyslexia will exist. That we cannot mix dyslexia into a single bag and hope to understand it. We have to diagnose specifically what the child has and specifically target different brain systems according to different deficits. Thank you very much for your attention.
Thank you very much, Stan.